Welcome to this walkthrough of problem number 1630, titled Arithmetic Subarrays. In this video, we'll explore the problem statement, break down the solution approaches, and analyze the complexity. Stick around to deepen your understanding and ace similar problems in the future. In this problem, you are given an integer array called nums and two additional arrays, L and R. Each L, I, and R, I, pair defines the starting and ending indices of a subarray within nums for the ith query. Your goal is to determine, for each query, whether the subarray extracted from nums can be rearranged to form an arithmetic sequence. Now, an arithmetic sequence is simply a sequence of numbers where the difference between any two consecutive elements remains constant. For example, sequences like 3, 6, 9, or 5, 5, 5 are arithmetic because the differences between consecutive elements are consistent. The input to the problem includes the array nums with a length of n, and the arrays L and R, each of length m. For the output, you need to return a Boolean array of length m, where each value is true if the subarray for that query can be rearranged into an arithmetic sequence, and false otherwise. To understand this better, let's look at the first example. Here, nums is 4, 6, 5, 9, 3, 7, and we have L as 0, 0, 2, and R as 2, 3, 5. For the first query, the subarray defined by L, 0, and R, 0, is nums, 0:3, which is 4, 6, 5. By rearranging this subarray to 4, 5, 6, we can see it forms an arithmetic sequence with a common difference of 1. So, the first result is true. For the second query, the subarray nums, 0:4, is 4, 6, 5, 9. Even after rearranging, it is not possible to form an arithmetic sequence, so the result is false. Finally, for the third query, the subarray nums, 2:6, is 5, 9, 3, 7. Rearranging this to 3, 5, 7, 9 forms an arithmetic sequence with a common difference of 2. So, the result is true. The output for this example is true, false, true. Now, let's consider the second example. In this case, nums is -12, -9, -3, -12, -6, 15, 20, -25, -20, -15, -10, with L as 0, 1, 6, 4, 8, 7, and R as 4, 4, 9, 7, 9, 10. For the first query, the subarray nums, 0:5, is -12, -9, -3, -12, -6. No rearrangement of this subarray can produce an arithmetic sequence, so the result is false. For the second query, the subarray nums, 1:5, is -9, -3, -12, -6. Rearranging this to -12, -9, -6, -3 forms an arithmetic sequence with a common difference of 3. Thus, the result is true. Similarly, for the third query, the subarray nums, 610, is 15, 20, -25, -20, which cannot form an arithmetic sequence, so the result is false. Continuing in this way, we analyze all the queries to produce the output, false, true, false, false, true, true. Each result corresponds to whether the respective subarray can be rearranged into an arithmetic sequence. To ensure a robust solution, it's important to account for edge cases. For instance, if there is only one query, the solution must handle it correctly for a single subarray. Another edge case is when all elements in a subarray are identical, such as 2, 2, 2. In this case, the sequence is arithmetic because the difference between consecutive elements is 0. For subarrays of length 2, they are always arithmetic since there is only one difference to consider. Finally, it's crucial to test the solution under maximum constraints. This means handling the largest possible input sizes, where n and m are both 500, and ensuring the algorithm remains efficient within these bounds. By addressing these scenarios, the solution will be both accurate and performant for all cases. To start, the brute force approach provides a straightforward way to tackle this problem. The idea is simple. For each query, we extract the subarray defined by nums, L, I, R, I, plus 1, and then check if it can form an arithmetic sequence. This involves sorting the subarray so that the elements are in increasing order, then computing the difference between consecutive elements to verify if this difference remains constant. While the method is intuitive and easy to understand, it's not efficient. The time complexity involves extracting the subarray in O, K, sorting it in O, k log k, and verifying the arithmetic property in O, k. When repeated 4m queries, the overall complexity becomes O, m asterisk k log k, where k is the average length of the subarrays. Additionally, it requires O, k, space to store each subarray. While the simplicity of implementation is a clear advantage, the inefficiency of sorting for every query makes this approach impractical for larger inputs or a high number of queries. Now, we consider an optimized approach that builds on the brute force method while leveraging key observations about arithmetic sequences to improve efficiency. In any valid arithmetic sequence, the difference between consecutive elements must be constant, and sorting ensures that the elements are in the correct order to verify this property. The process remains similar. For each query, we extract the subarray, sort it, calculate the common difference using the first two elements, and confirm that all consecutive elements share this difference. This approach retains the O, m asterisk k log k, time complexity since sorting still dominates, and it also maintains the O, k, space requirement for storing the subarray. However, it strikes a balance between simplicity and performance, making it a practical solution given the problem's constraints. It's both intuitive and efficient, particularly for the typical input sizes encountered in this challenge. There are some limitations to the optimized approach, as it still relies on sorting for every query, which is unavoidable under this method. To address this, we can explore an alternative mathematical approach that bypasses sorting entirely. Instead of rearranging the elements, we directly check if the subarray forms an arithmetic sequence using its mathematical properties. This involves calculating the minimum and maximum values in the subarray, then determining the expected common difference as max min /n1. By iterating through the elements, we verify whether all values are equally spaced according to this difference. This eliminates the need for sorting, reducing the time complexity to O, m asterisk k. However, this method introduces its own challenges. It's more complex to implement and may encounter precision issues when handling non-integer differences. While faster for larger subarrays, these trade-offs must be carefully considered. The strategy we choose for this problem is the optimized approach based on sorting. While the mathematical method avoids sorting and offers better time complexity, it comes with additional implementation complexity and potential edge cases, such as precision errors with floating point calculations. The sorting-based method, on the other hand, is straightforward and guarantees correctness, making it the most balanced option for this problem. The main trade-off is its reliance on sorting, but within the given constraints, this is manageable. For extremely large datasets, further optimizations, such as pre-computing ranges, could be explored. However, for most practical scenarios, the optimized sorting approach is both efficient and easy to maintain, offering a reliable solution to the problem. In this problem, we are tasked with determining if certain subarrays of a given array can be rearranged to form an arithmetic sequence. To break it down, an arithmetic sequence is a sequence of numbers where the difference between consecutive elements is constant. Given an array nums and a list of queries, where each query specifies the start and end indices of a subarray, our goal is to return a list of booleans. Each boolean represents whether the subarray corresponding to the query can be rearranged into an arithmetic sequence. To solve this, we'll explore two approaches. Starting with the brute force method, the first step is to extract the subarray for each query by slicing the array. Once we have the subarray, we sort it so that the elements are in ascending order, which makes it easier to check for constant differences between consecutive elements. Sorting, however, increases the computational cost, so we'll discuss its impact shortly. Finally, after sorting, we verify if the subarray forms an arithmetic sequence by checking the differences between consecutive elements. If all the differences are the same, we append true to our results, otherwise, we append false. To continue with the brute force approach, after sorting the subarray, we calculate the difference between its first two elements. This difference, which we call diff, serves as the key property for an arithmetic sequence. We then iterate through the rest of the sorted subarray, verifying that the difference between each pair of consecutive elements matches diff. If any difference deviates, we conclude that the subarray cannot form an arithmetic sequence. For subarrays that pass this check, we record true, otherwise, we record false. This process is repeated for every query. However, this brute force approach has a significant computational cost. For each query, we extract the subarray in O, K, time, sorted in O, K asterisk log, K, and check differences in O, K. If there are m queries, the total time complexity becomes O, m asterisk K asterisk log, K, where K is the average size of the subarray. Additionally, we use extra space for the temporary subarray and its sorting, resulting in a space complexity of O, K. While this approach works, its inefficiency for large inputs motivates the need for a more optimized solution. To optimize the solution, we leverage pre-processing techniques to reduce redundant computations. First, we use a prefix sum array to pre-process the input nums. This allows us to calculate the sum of any subarray in constant time, O1. Efficient range queries like this are crucial because they eliminate the need to repeatedly slice the array. Additionally, we pre-process a frequency map for each subarray to verify if all elements are distinct. Distinct elements are a key requirement for forming an arithmetic sequence, as repeated values can break the constant difference property. Once pre-processing is complete, we iterate through each query and compute key metrics for the specified subarray. These metrics include the maximum and minimum elements of the subarray, which help us calculate the expected common difference D. The formula for D is max_element min_element /n1, where n is the number of elements in the subarray. If D is not an integer, we can immediately conclude that the subarray cannot form an arithmetic sequence, and we append false to the results. This eliminates unnecessary checks for invalid subarrays. If the common difference D is valid, the next step is to verify whether the subarray elements can form an arithmetic sequence. To do this efficiently, we use a set to track the expected values of the sequence. The set allows us to quickly check if each element of the subarray matches the expected values. Using modular arithmetic, we calculate where each element should fit into the sequence based on D, the minimum value, and the total number of elements. If any element is missing or duplicates exist, we append false to the results. Otherwise, if all expected values are present and distinct, we append true. Once we complete this verification for all queries, we return the final result list. This optimized approach avoids the costly sorting step by relying on mathematical properties and pre-processing. By focusing on the key invariant, the common difference D, we ensure that our solution is both efficient and scalable for larger arrays and queries. The optimized algorithm significantly reduces complexity by eliminating redundant computations. Its time complexity is O, m*n in the worst case, where n is the size of the input array and m is the number of queries. This is an improvement over the brute force method for scenarios with large arrays and multiple queries. The space complexity is O, n, accounting for the pre-processing data structures like the prefix sum array and frequency map. As we conclude, it's important to consider edge cases. A single element subarray always forms an arithmetic sequence, while subarrays with non-divisible differences, where max, min, %, n1 equals 0, cannot form one. Identical elements, such as 5, 5, 5, may still satisfy the condition, and empty inputs must be handled gracefully. Lastly, for large inputs, the algorithm's pre-processing ensures scalability, making it a robust solution for this problem. By leveraging mathematical properties and efficient data structures, we achieve a balance between correctness and performance. This Python implementation solves the LeetCode problem number 1630, Arithmetic Subarrays. The problem requires checking whether specific subarrays of a given list can be rearranged to form an arithmetic sequence. Let's break down the code. 1. Initialization *. We define a method check arithmetic subarrays inside the solution class. The method takes three inputs, nums, the input array, and L and R, two lists representing the start and end indices of the subarrays to evaluate. 2. Result storage *. An empty list result is initialized to store the Boolean results for each query. 3. Processing each query *. A for loop iterates over the indices of the L and R lists. For each query, the subarray is extracted using slicing, nums, L, I, R, I, plus 1. 4. Sorting the subarray *. To check for an arithmetic sequence, the subarray is sorted in ascending order. This ensures that the differences between consecutive elements can be easily checked. 5. Arithmetic sequence check *. A variable is_arithmetic is initialized as true. The common difference of the potential arithmetic sequence is calculated as subarray 1, subarray 0. A nested loop iterates through the sorted subarray to verify if the difference between consecutive elements remains constant. If any difference deviates, is_arithmetic is set to false, and the loop breaks early. 6. Appending results asterisk. After processing the subarray, the result, true or false, is appended to the result list. 7. Returning the results asterisk. Once all queries are processed, the result list is returned containing the Boolean values for each query. This solution is efficient for queries because sorting each subarray dominates the time complexity. Sorting has a complexity of O, k log k, for a subarray of size k, and this is done for each query. The approach is simple yet effective, leveraging sorting and a linear check to validate arithmetic sequences. Here, we begin implementing the solution by defining the method checkArithmetic Subarrays, which takes 3 parameters, an integer array nums, and 2 integer arrays L and R. The goal is to determine if the subarrays specified by the ranges in L and R are arithmetic. First, we create a list Boolean called result to store the outcome for each query. Next, we iterate through the indices of the L and R arrays using a for loop. For each query, we extract the subarray from nums using the start and end positions specified by the current elements of L and R. The arrays.copyOfRange method is used here to create a new array containing the elements from start to end inclusive. Once the subarray is extracted, we sort it to simplify the process of checking for an arithmetic sequence. After sorting, we initialize a Boolean variable as arithmetic to true, assuming initially that the subarray forms an arithmetic sequence. We also calculate the common difference, diff, by subtracting the first 2 elements of the sorted subarray. Then, using another for loop, we iterate through the subarray, comparing the difference between consecutive elements. If at any point the difference doesn't match the expected diff, we set isArithmetic to false and break out of the loop. Finally, we add the result of this check to the result list. After processing all the queries, the method concludes by returning the result list, which contains a Boolean value for each subarray indicating whether or not it forms an arithmetic sequence. This implementation ensures that we efficiently handle each range query, extract the relevant subarray, and perform the necessary checks to determine if it meets the criteria of an arithmetic sequence. To start solving the problem, we initialize an empty list called result to store the outcome of each query. For the first query, we use the values L, 0, equals 0 and R, 0, equals 3 to define the subarray range. Extracting the subarray from the input nums gives us nums, 0:3 plus 1, which evaluates to 3, 6, 9, 12. Since this subarray is already sorted, no further action is needed to arrange the elements. Next, we need to determine whether the extracted subarray forms an arithmetic sequence. First, we calculate the common difference, which is the difference between the first 2 elements, 6, 3 equals 3. Then, we iterate through the subarray to verify if this difference holds between consecutive elements. For j equals 1, the difference 9 is 6 matches the common difference of 3. Similarly, for j equals 2, the difference 12, 9 also matches. Since all differences are consistent, we confirm that the subarray is arithmetic. Therefore, we append true to the result list, making it true. The output for this query is true. Now, let's consider another example where the input nums is 1, 3, 5, 7, 9, and the query range is defined by L, 0, equals 1 and R, 0, equals 3. We initialize result as an empty list again. Extracting the subarray using these indices gives us nums, 1:3 plus 1, which evaluates to 3, 5, 7. Since the subarray is already sorted, we proceed to check if it forms an arithmetic sequence. The common difference is calculated as 5, 3 equals 2. Iterating through the subarray, we verify for j equals 1 that 7, 5 equals the common difference of 2. As all consecutive differences are consistent, the subarray is confirmed to be arithmetic. With the subarray verified as arithmetic, we append true to the result list, making it true. The output for this query is true. Next, we analyze an example with multiple queries. For the input nums equals 10, 20, 30, 40, 32, the first query is defined by L, 0, equals 0 and R, 0, equals 3. Extracting the subarray gives nums 0:3 plus 1 equals 10, 20, 30, 40, which is already sorted. Calculating the common difference, 20, 10 equals 10. Iterating through the subarray, we verify that all consecutive differences 20, 10, 30, 20, and 40, 30 match the common difference. Therefore, we append true to result, making it true so far. For the second query, defined by L1 equals 1 and R1 equals 4, the extracted subarray is nums 1:4 plus 1 equals 20, 30, 40, 32. Sorting this subarray results in 20, 30, 32, 40. Calculating the common difference gives 30, 20 equals 10. Checking consecutive differences, we find that 32, 30 does not equal 10. As soon as we encounter this mismatch, we determine that the subarray is not arithmetic. Thus, we append false to result, making the final result true, false. The output for this example is true, false. Here, we analyze the time complexity of the solution step by step. First, the outer loop processes each query. If there are Q queries, this contributes Q to the time complexity. Next, for each query, the solution extracts the subarray nums L, I, R, I, plus 1. The slicing operation has a time complexity of K, where K is the size of the subarray, which is determined by R, I, L, I, plus 1. Summing up the slicing costs across all queries, the total contribution is N, where N is the size of the input array. Then, the algorithm sorts the extracted subarray. Sorting a single subarray of size K takes K log K time. In the worst case, assuming all queries involve disjoint subarrays, the sorting step contributes N log M, where M represents the average size of the subarray. These steps form the foundation of our time complexity analysis. After sorting the subarray, the solution checks whether it forms an arithmetic sequence. This step involves iterating through the subarray, which takes K time for a subarray of size K. Summing this cost across all queries, the arithmetic sequence check adds N to the total time complexity. Now, combining all the steps, the overall time complexity can be summarized. In the best case, where subarrays are small or already sorted, the complexity is N plus Q. However, in the worst case, when subarrays are large, sorting dominates, leading to a complexity of N log M plus Q, where M is the average subarray size. This breakdown highlights the efficiency of the solution under different scenarios. Now let's consider the space complexity. For each query, the algorithm creates a new subarray. The space required for this is K, where K is the size of the subarray. Across all queries, the maximum memory used is determined by the largest subarray size, denoted as K_max. Additionally, the sorting operation uses auxiliary space, and for Python's timsort algorithm, this also requires K for a subarray of size K. Again, the peak auxiliary space usage corresponds to the largest subarray size, resulting in K_max. Finally, the result array stores one Boolean value per query, contributing Q to the space complexity. Combining these components, the overall space complexity is K_max plus Q in the worst case. This ensures the algorithm is space efficient, even for numerous queries. To better understand the improvements, let's compare this solution with a naive approach. A brute force method might involve generating all possible subarrays from nums and checking each one for arithmetic properties. This would lead to a time complexity of N cubed in the worst case, where N squared is required for generating subarrays, and N is spent checking each one. In contrast, the optimized solution focuses only on the subarrays defined by the queries, efficiently slicing and sorting them to reduce redundant computations. While the current solution performs well for moderate inputs, it can be further optimized for very large inputs by avoiding sorting or using techniques like hash maps to cache intermediate results. Mathematically, the dominant term in the time complexity comes from slicing, sorting, and checking arithmetic sequences, combining to N log M plus Q. This clear breakdown demonstrates the significant improvement over naive methods and highlights the efficiency of the approach. When solving the arithmetic subarrays problem, there are several common mistakes to watch out for. First, overlooking edge cases for single-element subarrays can lead to incorrect results. Remember, by definition, a single-element subarray is always an arithmetic sequence, so it should return true without additional checks. Next, inefficiently extracting subarrays during queries is a frequent performance bottleneck. For example, repeatedly slicing the array for each query can be computationally expensive, especially for large datasets. Instead, consider methods that minimize redundant operations, such as pre-computing intermediate results. Another common pitfall is incorrect sorting logic. Sorting alters the original order of elements, so it's essential to work on a copy of the subarray to avoid unintended side effects. Additionally, some solutions fail to validate query indices. If the indices L, I, or R, I are out of bounds, this can lead to runtime errors. Always ensure these values fall within the valid range. Finally, floating point precision issues can arise when working with differences or averages, particularly when dealing with very large or small numbers. Whenever possible, use integer arithmetic to maintain precision and avoid such errors. Now, let's explore some insights that are particularly useful in interviews. Recognizing patterns is key. Many array manipulation problems benefit from preprocessing to save time during query evaluation. For instance, pre-computing sorted subarrays or calculating differences beforehand can significantly reduce redundant computations. When it comes to trade-offs, sorting subarrays for every query might seem simple, but it can quickly become inefficient for larger inputs. Instead, explore pre-processing techniques or hash-based methods to scale your solution effectively. It's also critical to clarify constraints during interviews. For example, ask about the maximum size of the input array or the range of queries. This information helps you decide when to use a brute force approach versus a more optimized solution. Another tip is to think incrementally. Start with a brute force method to confirm your understanding and correctness, then optimize step by step. This approach not only ensures clarity in your solution but also demonstrates strong problem-solving skills. Additionally, you can draw inspiration from related problems. For instance, LeetCode 560, subarray sum equals k, emphasizes subarray calculations and hash-based optimization. Problems like LeetCode 238, product of array except self, and LeetCode 525, contiguous array, highlight preprocessing and prefix sum techniques, while LeetCode 1094, carpooling, focuses on handling ranges efficiently. There are also alternative approaches that can be valuable depending on the problem constraints. One method involves pre-computing differences. Instead of slicing and sorting subarrays for each query, you can compute the differences between consecutive elements once. This allows for constant time checks to verify if a subarray is arithmetic. The trade-off here is extra space for storing these differences, but it significantly reduces the time complexity for multiple queries. Another approach is using range queries with segment trees. With a segment tree, you can process queries efficiently and check if the differences across a subarray are consistent. While this method is optimal for scenarios with numerous queries, it's more complex to implement. Finally, hash-based validation is another powerful technique. By storing the differences of elements in a hash set, you can check for uniformity without sorting. This approach avoids the overhead of sorting and is particularly effective for larger subarrays. However, it may not be as intuitive as sorting for some, especially when dealing with unordered data. Each of these methods comes with its own trade-offs, so choose the one that best fits the problem requirements and constraints. Great job making it through to the end. We've summarized the key points, walked through the approaches, and highlighted important takeaways. Stay curious and keep practicing. Don't forget to like, share, and subscribe for more coding solutions. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!